Have you ever just watched a quarterback throw that perfect spiral? Or a basketball player sink a three-pointer and the ball just swishes through the net? I mean, that arc. It almost looks like magic, doesn't it? Well, it's not. It's actually pure physics. And today we're going to uncover the hidden blueprint, the, let's call it, secret code in physics that perfectly describes the path of any object you throw.
So, that's really the big question we're tackling. Is there some kind of master instruction set? You know, a secret code that can predict that whole beautiful arc from the second it leaves your hand to the moment it lands? And the answer is, you bet there is.
And what's so amazing is that all of that complexity, the launch, the upward climb, that moment at the peak and the fall back to Earth, it can all be boiled down to one single, elegant master equation. So first, we're going to build that equation piece by piece, and then we're going to use it to crack a code.
Okay, so to understand the whole journey, the trick is to split it in two. You have to think of it like this. Any thrown object is basically living a double life. It's making two totally separate journeys at the exact same time.
And this really breaks down that double life perfectly. So horizontally, the ball is just on a cruise. It's just coasting along at a constant speed, no fuss. But vertically? Oh, vertically, it's in a full-on battle with gravity. It rockets upward, it slows down, it hits that peak, and then gravity wins and pulls it back down. And those letters you see? Well, U is just the initial speed you throw it with, theta is the launch angle, and G is the constant pull of gravity. It's these two simple motions happening together that create the arc we actually see. All right, so we got our two separate stories now, the horizontal cruise and the vertical battle. It's time to weave them together. We're going to build our master equation, one that can describe the entire path without even caring how long the object was in the air. You know, the logic here is actually beautiful. We've got one equation that tells us where the ball is horizontally at any given moment, and another for where it is vertically. So what's the one thing that connects them? It's time. Time is the one thing both journeys share. So if we take that simple horizontal equation and solve it for time, we can then plug that right into the vertical equation. And just like that, we get rid of time and we're left with a direct link between the ball's height and its distance. And this is what you get. This is it, the equation of trajectory. This is our secret code. I know, it looks a little intimidating at first, but what it's telling us is incredibly powerful. It's saying, look, if you just tell me how far the ball has traveled forward, that's the x, I can tell you exactly how high it is, that's the y. All you need to know up front is the launch angle and speed.
Now check this out. If you look at the structure of our physics equation, it's a perfect match for the mathematical definition of a parabola. See? It's got the form y equals some number times x minus another number times x squared. This is the proof. It confirms what our eyes have been telling us all along. The path of a projectile is a perfect, beautiful parabola.
Okay, so we have the code, but what good is a code if you can't use it, right? So let's take a sample problem and use our new master equation like a decoder ring to uncover the secrets of a throw. So here's our mystery. We've been given the equation for one specific projectile's path, but we have no idea how it was thrown. Our job is to play detective, work backwards, and figure out the original launch angle and the initial speed. And the method here is actually surprisingly simple. All we do is line up our mystery equation right underneath the standard master equation we just built. And from there, all we have to do is match the parts that correspond to each other. Let's start with the first piece of the puzzle. In the standard form, the part that's multiplied by x is tan theta. In our given equation, the part multiplied by x is the square root of 3. Well, if they're in the same spot, they must be equal. So tan theta has to equal the square root of 3.
And if you remember your trigonometry, or just pop it into a calculator, the angle that has a tangent to root 3 is exactly 60 degrees. And just like that, we've decoded the launch angle. One secret down.
All right, now for the second half of the code. We do the same thing, but this time we match up the x squared parts of the equations. We already know the angle is 60 degrees, so we can plug that information in, and the only thing left that we don't know is u, the initial velocity we're looking for.
So, after you run the numbers, we find that the initial velocity, u, was 40 meters per second. And there you have it, code cracked. We started with nothing but the shape of a path, and we uncovered exactly how it was launched. Pretty cool, right? Awesome. Now that we've really gotten our hands dirty with the main equation, let's lock in a few crucial ideas with a quick lightning round. These are key relationships that pop up all the time.
First up, think about the total time a ball is in the air
versus just the time it takes to get to the very top of its arc. What's the connection there?
The key here is just simple symmetry. The total time of the flight is exactly double the time it takes to reach the peak. Why? Because the journey up is a perfect mirror image of the journey down. Simple as that. T equals 2t.
Okay, this one's a classic. If you want to throw a ball as far as you possibly can, what's that one magic angle you should launch it at to get the max distance?
And the answer is 45 degrees. It's the absolute perfect sweet spot. If you go any lower, it just hits the ground too soon. If you go any higher, yeah, you get more height, but you're sacrificing that precious horizontal distance. Okay, final round. And this one's a bit trickier. Imagine you throw something so that the highest point it reaches is the exact same number as the total distance it travels forward. What specific angle could possibly make that happen? The answer is when the tangent of the angle equals 4. It's a very specific relationship that gives you a super steep launch angle of about 76 degrees. I think this is a fantastic example of how these equations can predict these really specific and kind of non-obvious outcomes.
So let's just wrap this all up. What are the big things to take away from all this? Well, first, remember that every throw, every toss, every launch follows that perfect parabolic path. Second, we have one master equation that describes that entire path. Third, we can use that equation like a code to figure out the secrets of the launch. And finally, knowing a few key rules of thumb, like the 45-degree rule, can help you solve problems in a snap.
But I want to leave you with one final thought. Our entire beautiful, perfect, parabolic world assumes one huge thing, that we're throwing in a total vacuum. Now, it works incredibly well for heavy, slow objects, but what happens when you introduce the messy, chaotic force of air resistance? How does that change the secret code? Well, that's something to ponder for next time.